Okay, today, rather than zoom into a specific study, I've decided to take you on a little tour, a journey through a decade of my research, part at least of my research. Start from when I accidentally fell into the world of the Green Sahara. It was like midday through the journey of my life. I found myself in an obscure wood. I think that one was Dante, but anyway, me was in this obscure place. Not metaphorical in the sense that I was in Stockholm and it was winter, so it was pretty obscure. So it was pretty dark, getting dark at 3 p.m. and I was invited for a coffee from a colleague of mine. And she mentioned that she had some simulation she had sort of greened the Sahara, the simulation of the Green Sahara for the Middle Holocene. And I wasn't really working on that at the time. And I asked her, if you green the Sahara, I assume you also have changed dust emission. And she said, actually not. And then I found out, I went back to my office and did some literature search, and I found out that no one actually had looked at the impact of dust changes during this period when, you green the Sahara, the major source of dust. I would have expected that there was some studies. So that was pretty much the beginning of a research journey that lasted 10 years so far, and I think still have some dunes to sort of cross. From there, then I moved into understanding the impact of vegetation and dust, not just on local climate, but also far afield, and eventually how this ties with today's massive afforestation project like the Great Green Wall of the Saudi Arabia Middle East Green Initiative. So, buckle up, we will be moving through time, space, and some dust as well, I guess. So, okay. So here a little bit of the outline. I would start talking about the past, the West African monsoon changes, the teleconnection associated with the changes in vegetation over the Sahara, the transition out of the Green Sahara, and then I will talk about these green initiatives. So probably it's like back in the days, like Heinrich Barth in his trip through Africa found different petroglyph in the middle of the Sahara Desert, and he wrote in his book artworks bear testimony to a state of life very different from which we are accustomed to see now in this region, because you can see from the middle of the Sahara, for example, in this cave, there are drawings of giraffes, lions, and we don't have those. He thought that those petroglyph was from the Egyptian civilization or some indigenous people. And he argued that this artwork must have been created long before the arrival of camels in northern Africa. Here we can see other location where we have been found caves with drawings. This is the swimmer cave. This one supposed they believe to be swimmers anyways in the middle of the desert, and here is in Chad as well, and there is cattle's drawings where today is pretty much in desert. And then here we can see a reconstruction of sapropel from the Mediterranean area, from the Mediterranean Sea, where we can see a period of greener condition. Here, this one here are the Green Sahara period for the last 200,000 years. And here we can see the change in summer in insolation through time, through the months, the seasonal cycle insolation 10,000 years ago relative to present. And we can see that in the summer months here we have an increased summer insolation relative to present day, and this is pretty much the driving force of this Green Sahara period. And here we can see from a paper of Raswani et al. In 2013 how the estimate of precipitation changes between the present day and the middle Holocene, the Holocene Green Sahara period. And we can see that, okay, here is like the precipitation, annual precipitation mean. And you can see that in the Sahara Desert, it rained less than 100 millimeters per year, and the vegetation is desert pretty much. But in the middle Holocene, it was like more a grassland and wooded grassland and woodland as well. And the precipitation went up to around 250 millimeters per year. And also there are other proxies show the African lake levels were increased. Here were higher, and here is the proxy reconstruction based on pollen. And we can see that, this is the estimate increase in precipitation, were around like 400, 600 millimeter in the center of the Sahara, where today we have about like 100 to 250 millimeter. What do the models say? If you look at CIMIC 5 or CIMIC 6, we see that we have, they do simulate an increase in precipitation. This is the annual precipitation anomaly. So we can see that there is this like blue means more precipitation, here means drier. So there is this shift northward of the intertropical convergence zone. The monsoon gets a little bit stronger. But if you actually look overall, the picture is well captured. But if you look in the details, then you will see that the increase in precipitation, for example, over the Sahara is it's not much. It's not even 50 millimeters per year. So not for sure, this is not going to green the Sahara. But the CIMIC model pretty much only account, at least the tier 1, like it's sort of account only for orbital forcing. They have dynamics, some of them have dynamic vegetation, but still initialized at 6K. Is not enough anyway. They don't get enough vegetation anyway, extension. And then here we can see like the seminal paper of Kutzbach in 1996, where they show for the first time that actually, changing the vegetation over the Sahara and also the soil, the soil moisture is actually leads to an increase in precipitation up to 28%. So this was the first study, and then we have another study in 2020 showing from Deepak and Dick Peltier, and they show pretty much that also if we account for lake feedback, soil and vegetation, what you see, this is anomaly in precipitation. You can see that when you account for all of them, then you get a quite larger increase in precipitation compared to the orbital forcing only. And then we go back to 10 years ago when I started working on this topic, and the colleague I mentioned was Chong Zhang. I was at the Department of Physical Oceanography at Stockholm University. And so we looked at the impact of dust reduction and vegetation change on the northward expansion. So here we have the anomaly in precipitation for the only orbital forcing relatively to the pre-industrial. We see a little greening. You can see the northward extension of the monsoon that goes from here to here, like a couple of hundred kilometers northward. But then when we green the Sahara and reduce the dust, then the monsoon extends all the way to the north. And when we only green the Sahara, the extension gets to around 26, and with the reduction of dust, it gets all the way to 30 degrees north. And here we see like a model intercomparison done from a former PhD student of mine, Shivangi, who didn't publish this one in particular, but anyway, you can see like the comparison of 4 different models: EC Earth, ICSM, CSM Toronto, and GES. This is only the orbital forcing. You can see that there is an increase in precipitation relative to PI. And then when you actually reduce the dust, when you change, the vegetation, in some cases you also reduce the dust, like in this case, in these other two, no, you can see this further increase in the West African monsoon. So like the take-home message of the local changes for the Green Sahara is when simulating the Green Sahara periods, vegetation, soil, lake, and dust feedbacks have a major impact on the strength of the West African monsoon. Vegetation feedback alone, through the albedo change pretty much, can lead to a northward extension of the West African monsoon of up to 10 degrees, and then the reduced dust concentration can further expand the West African monsoon for another 4 degrees, about 4 degrees. Then after that one, I started looking at teleconnections. So how this huge change in the West African monsoon can actually affect like climate elsewhere, or it's just, like confined to the Northern Africa locally. So what we see is here I show, we start looking at the El Niño Southern Oscillation changes, and here we can see the effect of over the Pacific of just orbital forcing. The orbital forcing leads to a reduction in sea surface temperature variability of about 10% in our modeling this year. Then when we green the Sahara, this reduction gets to 23%. And when we also reduce the dust, then we have a further decrease in the variability. So we kind of see that, the stronger the West African monsoon it gets, then the larger the decrease in variability is in the end. So, and how it works is pretty much the stronger the West African monsoon, the more you have a shift. You get less sort of an Atlantic Niño condition on this over the Atlantic, which is the Atlantic Niño is the little brother of the big Niño. Then we get like a worker circulation shift westward, and then this one leads to increase like easterly flow, so like a decrease, so westerly flow, so a decrease easterly, so a decreased trade winds, which deepen the thermoclines, and so there is less atmospheric and ocean coupling, which is the cause of the reduced variability. And then you see this, what is happening at the depth, and so you see that then you get like this sort of a La Nina condition during the winter months. And now, actually, I'm gonna present like a study that we just actually this one was just published is accepted by Shivangi, that have been looking at different models. It was in press in Communication, Earth and Environment. So we look at 5 different models, and here we can see the green Sahara minus the PMIP sort of experiments, and then we can see that all models show a decrease in the variability, more or less decrease, when you consider the green Sahara relatively to the reference simulation. And here we can see what is happening in terms of precipitation. You see all these models show a clear shift northward, and you also see the wind pattern here, shift northward of the ITC. And here, this is a work that I started 8 years ago. We just submitted this one when I was visiting Lamont. I was visiting Peter, and I was showing this result of the El Nino, that we sort of see this reduction also. If you look here, we don't only have a change in the Nino variability, but we also have a huge change in the Atlantic Nino, up to 46% when you go on the Green Sahara. So I told him, you have all tons of proxy. Do you have any proxy we can reconstruct sort of the variability in the Atlantic? Because we do have mean state, but we don't have actually the variability. And so he said, oh yeah, we may have something. And so eventually with Jerry Rustic, he started looking at some forums from the middle of the equatorial Atlantic. And finally we submitted the paper last week. And so what we see is that if we look at the Atlantic Nino variability through the lens of the foraminifera, we can see that the variability was sort of decrease around 5K, so around the end of the Green Sahara period, and then it started going up. Interestingly enough, we have we look at the transient simulation, the MPI, the Max Planck Institute transient simulation for the Holocene. And what we found was pretty interesting, that around that 4-5K, we also have a huge reduction in Atlantic Nino variability. And so it was higher before, then it goes down, and then it goes up again. And it sort of follow pretty much, what the proxy was showing. And here we can see also the Atlantic Nino the El Nino variability is seen by proxy in the Eastern Pacific and Central Pacific, like Ottawa's 2012. It's the blue line here, and then this color here is the Sahara white paper, where you also show a reduced variability here, here, and here. So you can see that you also have this a similar behavior in the Atlantic and the Pacific. So it seems they really like tied together. And also the model also, if you look at the Atlantic the El Nino, also showed this type of behavior. So then we tried to sort of figure out what was the cause. I mean, what was driving these changes in variability in the Atlantic at the end of the day. Because it might not have been just the West African monsoon changes, because it was actually happening at the end of the Green Sahara, and then anyway the variability goes back up. So it's while the West African monsoon wasn't going back up in terms of intensity, right? So what was going on? So actually we did like a correlation. We found out like the stream function. So it's pretty much, this is like a sort of what will look like this, the barotropic stream function and the surface. So it was pretty much like a proxy for the subpolar gyre in the southern Atlantic Ocean. And so we can see that there is, like, with a shift of 300 years, there is a correlation between the subpolar gyre in the southern ocean and the Atlantic Nino. You can see clearly here. So we found this connection between the Antarctic, sort of what is happening in the Southern Ocean, and that is then causing these changes in the variability into the Atlantic and Nino. Then we also look at the impact of changes of the West African monsoon intensity change, how this is actually going to impact, like the tropical cyclone. If you think about it, many of the cyclones in the Atlantic, tropical cyclones in the Atlantic, are formed out of African easterly waves. So if I'm gonna affect the intensity of the African easterly waves because I alter the monsoon circulation, well, maybe I'm gonna affect also the tropical cyclone. So what we see here is the track density changes. Is the track density. So we can see we have cyclone here, and then here. And then when we change the orbital forcing, then we have a sort of a shift, like in the Atlantic, like decrease here and increase towards the Caribbean. And then also we have this shift westward, so more inland of the tropical cyclones. And then also we have an increase in the southern hemisphere. So we can see this sort of a shift, like maybe it's the shift in the Walker circulation. Let's see if the case. And then we see when you green the Sahara, reduce dust, we have the same pattern. It's just intensified. Why? Because you have a stronger shift in the western, in the Walker circulation. And then with the Shivangi, we published another paper looking at the teleconnection between the West African monsoon and the South American island. So here we see that, okay, well, we intensify the monsoon there, but at the same time, we are going to dry the South America. This is the change in precipitation, and you can see that the stronger the West African monsoon, the stronger is the dry. And then, of course, we do a model intercomparison. We had 4 different models, and you can see that all models are pretty much agreeing that the stronger the West African monsoon, the stronger is the drying over South America. And you can see that what is happening here is I showed, like in the contour, we showed the upper velocity we had the shading is the upper velocity potential at 200 hectopascal, and the vectors show the changes in upper level divergence. So we see that here there is like a loft, there is this divergence, and then a conversion over here, and this is sort of justify the drying and the wettening, of course, in this region here. So the take-home message for the teleconnection is the momentum strengthening of the West African monsoon under green Sahara condition triggers a permanent Atlantic Niño with suppressed variability that shift westward the worker circulation, leading to a decreased ENSO variability and La Nina-like condition. Sahara greening and dust reduction can affect also the tropical cyclone activity. The stronger the West African monsoon, the stronger the westward shift in the worker circulation and the changes in the environmental variables affecting TC activities. Our results thus demonstrate that Saharan vegetation and dust emission are critical factors in driving ENSO response to insolation forcing, TC activity, and also Indian summer monsoon. I didn't show, but maybe Shivangi will start working on that one as well. We published a paper only using EC Earth, and we show that there is also an increase of the Indian summer monsoon due to the strengthening of the West African monsoon. And you can sort of relate it to this figure here, where you sort of have this increase divergence of, the more you here is stronger than here, so you can see that you get also a stronger Indian summer monsoon. And I discussed the impact on the South American monsoon. Okay, so regarding the transition, well, in 2000, the Manoval published this paper. It was like a record, a dust regional record from west of Northern Africa that show like an abrupt decrease in dust emission around 12,000 years ago, and then an abrupt increase in the regional fluxes right at the end of the African Humid Period. So it was sort of like hinting or suggesting that the transition in and out of the African Humid Period may well be abrupt, even though you can see here the insolation curve, the summer insolation curve, and you see that the insolation doesn't increase rapidly. It's a very gradual increase, and then you have a gradual decrease in the summer insolation. But the transition might well be abrupt, the onset, and here we see the withdrawal. But then a few years later, Cropling published a paper in Science from Lake Iowa. It's here in the middle of the desert in Chad, and what they were sort of showing was that the changes in vegetation around Lake Iowa was not that abrupt at all. It was actually gradual. So maybe the transition wasn't that abrupt. The point is that both proxy, they have their problems in a way. In the sense that like the dust fluxes, most of the Saharan dust comes from the Bodel Depression around the Lake Chad, or what used to be the mega Lake Chad. But it's a very shallow lake. So a little decrease in precipitation can actually, on the watershed, it can actually expose the area where the dust comes from. So, you start decreasing a little bit the precipitation, but you actually decrease a lot of, you expose a lot of desert area, and this is gonna give you the impression that actually the change was abrupt. On the other hand, here we are around the lake. Lake Iowa is like aquifer underground water. So, even if the change might have been abrupt, the aquifer is gonna respond in a very slower pace. And so it may give you the impression that the change was not abrupt. So anyway, the point is that is this transition eventually at the end of the day abrupt or not abrupt? Well, first of all, there was a paper in 2016 tried to actually link the desertification in the cooling in the Atlantic, in the Arctic, with the desertification. And so here they show that the cooling in the Arctic was enhanced by the termination of the African Humid Period. And on the other hand, this was a 2015 paper, 2015, and then in 2017, Collins et al. Published another paper instead, which they were saying that the cooling in the northern high latitude was actually responsible for the rapid termination of the African Humid Period. And so here this shows some proxy from this region here. And now with Shivangi, we are looking at how the enhanced West African monsoon amplify Arctic warming during the Green Sahara. So what we see is actually that we look at different climate model in which we green the Sahara. This is easy Earth, and you can see, for example, this is like the only orbital forcing. This is the Green Sahara condition, and you can see that the Arctic warming is enhanced when you green the Sahara. And all models actually show this one. So when you green the Sahara, you get a stronger Arctic. Even here, you don't get like only orbital forcing. In gas, you don't even get an Arctic warming. But when you green the Sahara, you do. And same here for the Halley model. Not much happening here. And then when you green the Sahara, you do get a warming. And look here, the interesting things is these three models show a warming in northern Africa due to the greening of the Sahara, but not these two. So it's not really the warming in the northern Africa that then is causing the warming, but probably it's the change in the West African monsoon that then eventually change the circulation and makes this warming happening in the Arctic. And then we did actually a sensitivity study to see if a couple of sensitivity studies using an atmospheric model only, in which we prescribed the easy Earth SSTs, like for the standard mid-Holocene PMIP. Here you can see the precipitation. You have this, you can see the precipitation. Then you see the Green Sahara. You have an increase in precipitation because we green the Sahara. And then here you can see the difference between the Green Sahara and the only orbital forcing. Okay, and so the sensitivity studies are the following. So what we did is to warm the Arctic, but keeping the Sahara dry. So what we did, we imposed the SSTs, the warm SSTs above 60 degree north. So we wanted to see if in dry Sahara condition, like a warm Arctic, because in the onset of the Green Sahara period, you change the insolation, so you increase the insolation, you warm the Arctic. Is this warmer Arctic able to feed back in the West African monsoon and sort of increase the strength of the West African monsoon? So if you look at a warm Arctic minus the only orbital forcing kind of thing, you see that there is no change. So the fact that we warm the Arctic seems not to have any effect on the West African monsoon. But so let's do the other way around. So at the end of the African Humid Period, when Collins et al. Were saying, okay, well, we cool the Arctic. The cooling of the Arctic is actually impacting the West African monsoon. It's actually drying the region. So let's see if that is the case. So what we did is cold Arctic plus Green Sahara. We were in the Green Sahara period, and let's compare it with the Green Sahara only. And then you can see that here the change is nothing is significant. And you can see the change between the cold Arctic case minus the PMIP. It's pretty much the same as the full Green Sahara. So it seems that no, the cooling of the Arctic is not able to feed back and impact the West African monsoon. This is a work in progress, and hopefully soon we'll be submitting it. So this other one was just a review paper where we look at past changes in future implication for the Green Sahara. We show pretty much, we compile all this record here from different area of Northern Africa. Here we show the latitude, the insolation changes, and we can see that most of the Overall, this is latitudinal average, 5-degree bins. Here are the high resolution kind of proxy, and these are all the Northern African records. So when we average, this sort of suggests like a sort of a smooth transition. But of course, there are areas where this transition appears to be more abrupt, and other in which it seems less abrupt. So while some paleoclimate archives show changes that took place over several centuries, an order of magnitude faster than the orbital forcing, others proxy actually show a much more gradual change. The withdrawal of the African humid period was time transgressive, like following the insolation changes, as also shown from team paper in 2015, I think, if I recall correctly, it was published in Nature Geoscience. And so the new transient climate simulation from MPI, you can see here. I will explain in a little bit what these figures show. But anyway, it shows spatially heterogeneous vegetation dynamic in Northern Africa, with the faster increases simulated desert fraction up to 7 times faster than the orbital forcing occur around 20 degrees north in the western part and around 14 north in the central part. So what you see in this figure is the transient simulation from MPI, from the MPI model. You can see the desert, the shrub, the grass, and the forest. Like this is the percentage, the amount of desert forest and so on. And then you can see that, like around 20 degrees north, you have sort of like a relatively abrupt, increase in desert area and like a rapid decrease of grassland. Because of spatial heterogeneity of the African landscape and the African monsoon circulation, abrupt changes can occur in several, but not all, regions at different times during the transition from humid to arid climate. Abrupt changes in one region can be induced by abrupt changes in other regions, a process that sometimes is called induced tipping. So the African humid period transition of the Sahara was regionally abrupt and is a tipping element with respect to changes in the driving forcing, which is like the solar insolation, but slow with respect to the time scale on individual humans and local ecosystem. In any case, the African humid period transition, rapid or gradual depending on the perspective, has led to persistent and long-lasting changes that are associated with a tipping point in human civilization, which led to emergence of new cultures along the Nile. So now let's jump into the future, we start gradually, like going towards the future at least. We go to the 1935, when Stebbing first proposed a forest belt between the Sahara and the Sahel. And this was meant to sort of reduce the southward advance of the Sahara and man-made soil erosion. So you can see that this is like Niger, Cote d'Ivoire, Ivory Coast here, and then you can see they sort of meant to build like a sort of a two-wall of trees. Then in the 1960s, the idea of incorporating trees as a useful infrastructure element in the landscape in the Sahel and the Sahara arose during this period. And then Thomas Sankara was the leader of Burkina Faso in the beginning of the 80s, sort of proposed this Great Green Wall as well. And he actually planted 10 million trees in his I think he was on power only for 3 years, and then he was killed. And his government was overthrown, and so everything died with him, so pretty much. But then in 2005, the proposal was revived by the Nigerian president Obasanjo in 2005, and in 2006, the Great Green Wall is approved by the African Humid Period. So in 2007 was officially adopted. So what is this? Ideally was a wall of trees extending from Senegal to Djibouti. So it's like 7,000 kilometer for like, initially was a 15 kilometer wide and 7,000 kilometer long. So why I decided to look at the Great Green Wall to start with? Well, I mean, I was doing studies in Paleoclimate, looking at the Green Sahara and seeing the huge impact that vegetation has. So I got just curious and said, well, what about those geoengineering afforestation projects that they've been planning? Can they have a local impact that we can see it, but also maybe an impact far afield? And so I started looking at the impact locally. But anyway, right now the project changed a little bit. It's not just like a belt of 15 kilometer of trees for 7,000 kilometers. It's more like a planting between the 100 and 400 millimeter precipitation area. And it's more like a mosaic with different landscape scale action that are designed to provide a long-term solution for improving environmental and socio-economic conditions in the zone. So you can see this is an example. There are like different patches with different things like reforestation and fodder plot, reforestation plot, fodder plot. So they are planting like Acacia Senegal of the Arabic gums, that they can actually use it. So it's also a way to keep the population to have jobs and and avoid or decrease the emigration. So, and you can see it here from satellite. You can see a mosaic here with different different action that has been doing here, and you can see they've been planting trees here, and here we can see the normalized NDVI here, and you can see that the area that have been green here compared to the area that are not green, and this is from northern Senegal here. So then we published this paper last year with another PhD student, and it's called on one earth, and was the contrasting consequence of the Great Green Wall, so easing aridity while increasing heat extremes. So what we use a atmospheric climate model, and we did different scenarios of greening of this belt, sort of, let's call it belt, like a low case scenario, medium and high case, and then an extreme case. And you can see here, this is the belt between 100 millimeter to 400 millimeter here in the Sahel region. And then you can see the low vegetation, medium vegetation, high vegetation, and extreme case, where we go all the way till 50 millimeter. And as you can see, the percentage of desert. So in the low case, what we did is pretty much shift the vegetation from here was the 400 to 300, and we put the vegetation that we have here, we put it here north, and then this one further north here. And then the medium high was further green, pretty much. So if we look, and then we did a future scenarios, 2.6, so now we are getting into the future at the end of the century. We do the 2.6 and 8.5 scenarios. And we don't see, in just the scenario without Great Green Wall, relative to present, we don't see a huge change in preceding West African monsoon intensity. But when we green, not the Sahel, when we have the Great Green Wall, this is relatively to the future scenario. So we can see that even if we started just greening with the low case scenarios, we do have an increased precipitation here. In the medium is even more, the dotted one means that the changes are significant. And then on the high one, you can clearly see the increase in the West African monsoon. And then in the extreme case, you actually get precipitation way outside the area where you green, in all northwestern, you can see the end of the wall is here, but you get quite some precipitation even on this area that is completely desert. And even here you get more precipitation significant in the southern part, not much in the northern part, but in the southern part it gets wetter. And if you go on the 8.5 scenario, the anomalies are pretty much the same. So the effect is independent from the climate state. And this is the temperature changes in the future. We go in the 2.6 scenarios, which is very optimistic. We only increase the temperature over Northern Africa of about 0.75, 1 degree. And in the worst case scenario, which is the more likely these days, anyway, we can see that an increase in temperature between 3.5 and 4.5 degrees. What happened to the summer temperature? The summer temperature sort of decreased because of the Great Green Wall. And you can see even up to 2 degrees in the extreme case. And this is the same for the SCP 8.5. But there is a but, because the summer is not the warmest season. The warmest season is the pre-monsoonal season. And you can see that if you look at the hot extremes, you have an increase. Even in the low case scenarios, you have an increase of 0.5 degree of the hot extremes. In the medium, you start getting towards 1 degree along where the wall is built, and here we get even up to 1.5, almost 1.5 degrees. So this is in the pre-monsoonal season, the extremes increase. And it's the same for the 8.5, we have a similar pattern. So the take-home message is that the Great Green Wall has significant impact on Northern Africa, increasing rainfall over the entire Sahel, even doubling the precipitation in its northern part. The consecutive dry days are also, I didn't show them, but are also substantially reduced, and the max 5 days precipitation are increased in the equatorial tropical Africa. Temperature around the Great Green Wall are decreased of up to 1.5 in summer and over 2.5 degrees in the extreme case. However, the hottest temperature become more extreme, up to 1.5. And the other thing is the heat stress also increases because the humidity increases. And so this is going to give you even much more than the 1.5 or the 1 degree increase in the extremes in temperature, in absolute temperature. The impacts are not confined to Northern Africa, but seems to extend into Southern Africa and also Europe, and also the Middle East, actually. And talking about Middle East, I also started looking at the effect of the Saudi Arabia Green Initiative, Middle East Green Initiative, where the Saudi Arabia prince sort of decided that he wanted to plant about 50 billion trees in the Middle East area, which is a lot of trees. It's really a lot of trees, and 10 billion just in Saudi Arabia. So we try to sort of what we did in order to plant all these trees. What we did is we started planting between 400 and 600 millimeter, and we go down up to 50 millimeter because otherwise there is no space to actually, because the idea is to plant 25% of the desert area will be sort of afforested. So we kept with that in mind. We went from 600 millimeter down to 50 millimeter, and then we keep at least and this is pretty much what we did. So it's we plant evergreen trees, deciduous, evergreen shrub, deciduous shrub, grass and desert with different percentages. And what we see, this is very preliminary result. We only have 10 years, we are running 30 years. So what we see here is the average change in precipitation in the present, in the future, and then when you do the Middle East Green Initiative, you can see here the temperature change. Let's see at the anomalies. And you can see that when you have the Middle East Green Initiative, you start warming here, but in the Middle East Green Initiative plus Great Green Wall, for some reason, the increase in temperature is less strong. Then here we can see the precipitation changes. And the interesting thing is that, when you do the Middle East Green Initiative, okay, you have a slight increase. You can see the color scale is not the best one to actually see it. But then when you do the Middle East Green Initiative plus the Great Green Wall, the increase over the Middle East is strong. And then here is in percentage. You can better see in percentage the increase here when you also bring the Sahara relative to this case here. The consecutive dry days, you can see that that you have this increase in consecutive dry days that is larger when you also clean the Sahara. And then we did another studies that is in preparation where we afforested only the area in the middle of the, and with this I'm going to conclude the trip. So we afforested this area here, and we also the thing is here we can you can see the leaf area index change and the vegetation fraction changes. And what you can see is the afforestation only gives you a warming, but then we did an afforestation plus irrigation where we put irrigation of 0.5 millimeter per day. So every day at 6 in the morning, we irrigated of like 0.5 millimeter. It's not a lot, but I mean for the region it is actually, but it's it's like 160 millimeter per year in total of rainfall, equivalent of rainfall. But you can see that the temperatures change free, so you actually get a cooling. And in terms of also precipitation changes, if you have also the irrigation, there is probably most moisture recycling, and then you actually can get more precipitation. So in conclusion, the Middle East Green Initiative increased the precipitation, and the consecutive dry days are also substantially reduced in the green areas. Temperatures are increasing in the forested region. However, if irrigated, the evaporation cooling offset the warming due to the albedo changes. So, and if Middle East Green Initiative plus Great Green Wall leads to further increase, well, not if, but Middle East Green Initiative plus Great Green Wall leads to further increase in rainfall over the Middle East. And so the overall take-home message is that, you know, the monsoon strength here is due to dust changes, vegetation changes, lake changes, water land use changes. It's going to affect the ocean changes are going to affect the monsoon strength, and the monsoon strength eventually is going to impact the Asian monsoon, tropical cyclone, El Nino, Arctic amplification, and so on. So I guess this if you fall asleep during the presentation, I guess if you wake up right now, you just look at this one, you pretty much get the gist of the talk anyway. Okay, I guess that's it for me. Do you have any question?